Okay, so I'm going to do three things. I'm going to talk a little bit about our paper that's in this journal, where we wanted to attack a question of how we compare actually networks, but in this case they're cities of vastly different sizes. And that has a very practical endpoint, as we'll see. The second thing I want to do is to talk about where some of this is going in mathematics. And the first thing I'm going to do, that's a sort of new topic area for all of us, which is becoming interdisciplinary. But nevertheless, this whole interdisciplinary area is going to drive some new and difficult questions in the mathematical sciences. So I'll talk a little bit about that. And I'm going to start off by doing a bit of mathematics on the grounds that what doesn't kill us makes us stronger. So we can all go away, have improved something this afternoon. When you look at cities, they've got a lot of similar infrastructure. We saw the clusters earlier in the talk. They've got a lot of similar infrastructure. They've got police forces, they've got ambulance guys, they've got electricity, power, schools, all of these sorts of things. They've also got people in them. And the network of who knows who really inspired some of this, because we wanted to say, well, are cities really the same? There's been a lot of work on scaling laws, and we'll have a look at those in a minute, just for a bit of fun. But actually, there's a harder question there. If I spend a huge amount of civic money making some intervention in a city, and it's successful, do I then move to the next city and do the same thing? Because it looks the same. It's got the same roads, it's got the same traffic, it's got the same. But is it really, given that there's a social dimension to these things? And I'm going to say that not all cities are the same, actually. That's where we're going with this. But on the assumption that they are pretty similar, this has been going on for a very long time, and Mike Batty and others have looked at the way that different type of things, it doesn't matter, you pick something and then you fit a scaling law to it, and some things scale sublinearly. So as the city grows, if we look across a whole range of city of different sizes, as the city grows, they scale sublinearly, and some things scale superlinearly. And great, so we can measure anything we like in a city, plug it on log paper, put a line through it, and we'll measure the happy.
That will smooth out an awful lot of variation if you log something.
Well, it does, yeah. Happy? Why should there be scaling laws? Why should there be power law scaling laws? Why? Sorry?
Increasing returns. That's where.
Yeah, well, you could have an exponential scaling law. Why don't we see that? Happy? Let's have a look. Let's consider a city as a graph. That's a gross simplification, but if they're going to be scaling laws, it's going to work for graphs. And let's rule out pathological cases. So Q is going to be something I measure. So it might be crime, it might be GDP, it might be whatever it is. Q is going to be something I measure. And it maps really a graph onto a real value R, which is normally positive between consenting adults. Let's let S1 and S2 be graphs on the same set of vertices. So that the edges of S1 are contained in those of S2. So that just means that S2 is like S1 with a few extra edges added. That's all it means. And then let's restrict ourselves to consider Q, where Q of S2 minus Q of S1 is bounded by the relative change in the number of edges. So this rules out some cases. Like now Q can't be, say, the number of distinct components. Because if I just add one edge, I can join two up, and this changes by an integer, but it might be 1 over a million there, or 1 over 10 billion. So this rules out cases like that. It's saying something a bit like continuity. But we can't talk about continuity for graphs because we can't continuously move from one graph to another, except in a limit where the graph is very, very large. But it's something like continuity with respect to the number of edges. We could use this to do some maths if we want, but we're not going to. This just means that if we want to form graphs, we can form up graphs any way we like, and we can add and subtract a few edges, and it won't matter very much, considering the measure we're making. So that's reasonable when we're looking at things like production and things like that. If you just add one or two edges in the graph, it shouldn't really make a lot of trouble. Disjoint unions. A union in maths is a nuisance, isn't it? Because if you've got a set ABC and a set CDE, you put them together and you don't count C twice. But in this you do. This is what we've always wanted, isn't it, for unions? We wanted to remember where they came from. So a disjoint union of a set S1 with S2 is really just put the two sets next to each other, and then you can relabel them if you like. So they remember where they came from. So you don't... This clearly works for graphs as well if we do the union on vertices. So if I have a graph here and I have another graph here and I just bring them together, that's a new graph. And it doesn't really matter if one vertex here was called the same thing as one vertex here. We just forget that and relabel the thing if we need to. Okay? Now, if we have a scaling law for this property Q over all the graphs S, then it really ought to work for a nice subset. And that is if you choose your favourites S, and I'm going to think of that as a ghetto or a community, then little ns denotes the disjoint union of n such communities, particularly n similar communities. We can generalise this later, but stick with me. If there's a scaling law, it really ought to work under these circumstances. And so given a community S, I could imagine a city as being just a disjoint union of a number n of those communities, and then because of the international rules of Q that we've already agreed, I can add a few edges in to join them up if I want, and it isn't going to spoil Q, right? Because we've agreed that Q is sort of continuous with respect to... Okay, so if we've got a scaling law, it ought to work for these. Now suppose there is a scaling function, so this would be like a power law in n or something. A scaling function that describes how the functional Q behaves for the disjoint union of isomorphisms, then it would have to satisfy this. Q of the disjoint union graph, NS, would have to be this function G of the value of Q just on S, and then the number of copies of S I had. That's what a scaling law does. And so we've made no progress at this point. This is all notation. Okay, and now comes the moment, you know, in the lecture where we just do something a bit cute. We try and say, well, what sort of condition does that put on G? Can G be anything? No, it has to satisfy a functional equation. Because if you apply G twice, G of Qn gives me Q of Sn. And then if I apply that with the same thing with m there, then that has to give me G of Qnm. So I just apply G twice. Standard trick. It's very exciting. This is a functional equation. And for those of you with maths and physics backgrounds, you'll know that functional equations always appear at very exciting times in the development of theories, like wavelets, like bifurcations off to chaos, all of those sorts of things. And in fact, functional equations predate differential equations, I'm proud to tell you. So before everybody was fiddling around with calculus and differential equations, this was the game. And it's really interesting today that when we see sort of renormalization type arguments in physics, in mathematics, that we get back to functional equations. So here it is. So, I mean, G has no choice but to satisfy this. G of Q of 1 is just Q, because that's just Q of S. So we've got an initial condition, and then we've got to satisfy this condition. And we can guess the solution to that. Here's one solution. Forget this bit on the right there. Q times n to the minus alpha. So that's Q times n to any number I like. So if alpha's negative, it grows like a power law. We've seen the power laws. If alpha's positive, then it will decay. And you can add this extra term on for free. Doesn't give you any problem. Adds an extra constant in. This is one of the general solutions of this equation 3 with its boundary condition there. And you can immediately see that if alpha's positive, then as n goes to infinity, this will tend to a constant beta. So this is just a saturating function which just grows up and is asymptotic to a fixed constant beta. The other alternative is the thing just grows like a power law and goes on. Very satisfactory state of affairs. Are there any other solutions? Sadly, yes, there are. Q to the n is a solution. That's exponential growth. So why don't we see Q to the n when we go over the work of in this area? We don't tend to see this. There's a very good reason. Here's one good reason. It's called the semigroup property. If you fiddle around with this, you sort of want to define n as e to the, I know n is discrete, but don't worry about it. If you define u as log n, and then write h of qu then h satisfies this equation, which says h of q of u comma v is just, and this is the semigroup property. So we know how to solve this. We can go and get a solution of any semigroup, and then we can construct a solution for h, and so therefore we can construct a solution for g. Where do semigroups come from? They come from ordinary differential equations. The bottom line of this, it says that if you have a differential equation, then very often you're in the realm of a rest point. And when you're in the realm of a rest point for a differential equation, the growth is exponential, because you've got eigenvalues and things, that the linearized system there, right? And exponential growth corresponds exactly to the solution we've already seen. So one argument is that power laws in observations of functionals on networks are really as ubiquitous as the exponential is in telling us how solutions of ordinary differential equations. We could construct, the sharp-eyed amongst you'll see one later, we could construct a functional which had an exponential power law growth. It would have a very peculiar differential equation, but this is the reason we're seeing power laws ubiquitously. And if we see them just on, it's just a property of scaling of networks. Okay, and then if we measure, Q can be pretty much anything which is broadly continuous. Next question, for which Q do power laws exist? Simple solution to that. If Q satisfies this equation, so S0 is a graph, and then S1 and S2 are other graphs, so we do the discrete union, and when I perturb S0 twice by S1 and S2, then the change in Q is bounded by the difference in the Q's of S1 and S2. This looks like and is a Lipschitz condition. So Lipschitz continuity is a slightly stronger version of continuity than the thing we saw early on. And Lipschitz continuity always occurs in maths when we're looking for existence. And this is good enough. The proof I'm not going to go through, but it's really quite interesting because you kind of prove it by contradiction. You say, well, if a power law doesn't, if scaling law doesn't exist, that must mean there are two graphs which are indistinguishable up to n minus 1 copies of each of them, and then the nth copies of each of them are distinguishable. And you can pull out a contradiction from that. So in actual fact, this works for a very, very large set of Qs. In particular, if we take any matrix M associated with S, like the Laplacian or the adjacency matrix, then when we put discrete things together, we've got a sort of block diagonal structure. If we take a function of that, well, that's just a function of a matrix. And usually a function of a matrix is just monkeying about with the function of its eigenvalues. And so it turns out that all of those would satisfy this kind of condition, as long as we had reason. So actually, there are, almost anything we can think of in algebra would have a scaling law, and almost all of those scaling laws are like power laws. In fact, you have to work very hard. There's a trivial one where you take the determinant of a matrix. Coming back to structures, so I talked about there a city as decomposable into subcommunities, and that's the nature of this work, which I've done with Tamsin Lee, who's been a postdoc with me for a number of years. So just have a quick look at that. Cities and multiplexes. Here is the data. So this data is up on the Royal Society site, and I'll explain what it is. These are reciprocated mentions networks on Twitter. So let's pretend we're doing it for the whole country. So if I at Mirko, and within 4 weeks Mirko ats me, then we've both sent a message, public message, to each other preferentially. We must know each other, really. Or I could say, well, let's do it twice, and twice. So there's some reciprocation. Now, I'm always sending ats to Wayne Rooney, and he's never responded. I've got a lot of advice for Rooney, especially as he's getting a bit older. Needs to drop back a bit. So that's what we've done here. So you only know someone if there's a reciprocated mention over a certain time period. And then we've taken all the geolocated people in these top 10 cities of the United Kingdom. So we saw a lot of these in your networks. You had quite a lot of Liverpool. I'm a lifelong Manchester United supporter, so there's no Liverpool in this talk, nothing for Liverpool. Okay, some of them are quite small. So the Edinburgh is, a few thousand. It's really a tenth of the size of London, which I'm not even showing you here. I'm just going up as far as Manchester. So this is just a sample of these networks. Now, I have produced data for the top 100 cities and towns in the country, and I'm going to make this available to each university can have their own data. I'm having a bit of trouble with that data set at the moment, but when I've done it, because of course we're all getting into smart city territory, and so it's really nice if people can have a view, and especially comparatively, as to where their city sits with others. So we're trying to do that. For the moment, with this paper, we've just worked on these 10 cities, so all of this is there, and there's a nice file where you can pull these reciprocated mentions down and do whatever you like with them. But these cities somehow reflect the social connections within a certain strata of self-appointed Twitter users, and it doesn't really reflect anybody else, okay? So this is not the extent of this, but it's still quite interesting because there are quite large differences in these things, even though, by eye you might say, well, they've got blobs, and some of these are driven by, there are 3 universities in Cardiff now. We could imagine that kind of thing, couldn't we, driving this, or Leeds, got a lot of rugby union teams in Leeds, a lot going on there. Okay, this is something that we don't have to fight about today. So this is called splitting a city up into modules, and almost, if you've got 3 network scientists, they've got 9 methods to do this. So let's just choose our favourite method, whatever it is. So here I've taken the sainted city of Bristol, wonderful place, yeah, Bristol, love Bristol. And what I've done, I've split it up by, in this case it's by modularity into probably 70 odd cities. I can't remember how many we've got, it doesn't matter. Actually, this is modularity, which gets optimized. This is something else, this thicker line. You can see that most of the work's done by the time we've got round to about here. And then we're forced to moronically go on and on. We must be fitting noise at this point, right? Right. So, I always advise people, to set some sort of stopping rule, which, where you've got something which would be robust to noise, and you could check that if you wanted to. That wouldn't be such a bad thing, would it? So here we go. Comparing different cities is then very easy. If you want to know the details, read the paper. But you take a city, say Leeds, you decompose it however you like into its sub-communities, and then you put all those in a bag. And then you draw out, with repetition, communities. And you keep going until you've made something the size of Bristol, and then you can join it up a little bit if you fancy that. So then you've made something the size of Bristol out of all the components of Leeds. And you do that 1 billion times. That's a very honourable moment, because the computer's doing our work for us. And then we can calculate any performance measure we like over the ensemble of Bristol-sized cities made of Leeds components. And we can also calculate it based on true Bristol. And we can decide whether Bristol sits in the envelope of Leeds-based Bristols, if you like. I should have chosen something else other than Bristol, I feel, but there we go. Okay, so that's what we're doing. And then if it falls inside the envelope, you say, well, that's quite good. If we did something in Leeds, it really looks very similar to Bristol, because we can do it the other way as well. We could, But if it falls outside the envelope, you need to say, well, you know, whatever we did in Bristol, that won't work in Leeds, because Leeds is definitely different. There are fundamental things in Leeds that cannot be replicated by knowledge of Bristol. So beware town planners or councils or about to spend large amounts of money. What we'd really like to do is to put all the cities into some sort of equivalence class, wouldn't we? So that, you know, you cities can look at each other and look enviously at the other cities, but they're not for you. You're in there. And to give a sort of comparison set for cities, even though they're very different sizes. And of course, we want to do this about as far as 100. That takes us down to Guildford is the last one. So University of Surrey just sleeping in there. Great stuff. This is what the sort of stuff looks like. So let me take an example of Bristol here. So here's Bristol, and I'm constructing cities. Bristol itself is bang on. I'm constructing cities, and Leeds falls well outside the Bristol envelope. The green shows the Bristol envelope. So really, actually, there are at least 2 equivalence classes in this data. And we tried to have a little look at that graph and to speak about it. Okay, I've just got a couple of minutes left. I just want to talk about a new topic for us. So whenever we get into an application, in this case, it's urban analytics and cities, we end up talking about approximations because we know we haven't got all the data. We know the data's got false positives and false negatives in. We might want to make calculations that are very expensive and things like that. So a lot of our work really has been about looking at approximations of what, you know, if I know what I want to calculate with the real data, can I approximate that with an easier network to make the calculation easier whilst minimizing the error I'm making? So a lot of this has gone on the quiet, mean field theory, a lot of the stuff we do when we talk about dynamics of networks, where we're really looking at stochastic Markov chains, increasing the measurements of centrality really like that. If you really knew what you wanted to calculate, you could probably simplify the city and have a, you know, this has gone on for years in applied maths. It's called asymptotic analysis. We form the differential equation up and then we split it up into problems we can solve and then glue them back together again. Right? And network analysis has got to the point where it really needs that next step. You know, a group of us in the UK ought to get together and show some leadership before they do it in California. So what with all of this? So it's clear that all cities are not the same, and that clearly impacts on policy, which is a big outball for us. How do cities change over a year? When are they disconnected? Got this great project in Oxford where they look at the sliding doors, the different communities that move through the same spaces. You know, if you take the university out, we're a sort of market town with low educational achievement. You know, terrible things going on up the Cowley Road. You know, there's a lot of problems in Oxford, and we're sliding past different communities. We're occupying the same space. And so I really wanted to get to things like that. I love the idea of having safe spaces for people to walk home at night. You know, as soon as we get real smart cities, that's what they're going to do for us. They're going to look after the citizen. Not the town planners, not the people in Civic Hall, benefits to the citizen, direct benefits to the citizen.
You really haven't ever acted with Oxford City Council, have you?
Well, I have actually. Yeah, I have. And I mean, you know, they're going very slow on some of this stuff because they haven't got any money. That's the bottom line of it. All right, smart city projects are almost always about show and tell devices. And actually there's two-way dividend here. I think we have to observe and drive new analytics from observing cities. And that really does mean humbly observing cities. But then we have to deploy those analytics and think of ways they're going to make a social change. I think a lot of our analytics just gives us a warm tummy feeling, you know, great, we've written the paper in the Royal Society, you know. Actually, we really want to get some impact going out of this, and that's what the ATI wants too. GCRF, Global Challenge Research Fund, the UN Strategic Development Goals, this can't happen without urban analytics and urban environments because so many people are gravitating to urban environments and to cities. So it's a big area in this, and I think that data science in particular, our sort of mathematical science, has to take its place in that. And the universities and the ATI need to become aligned with these sorts of projects, multidisciplinary expertise, and we need to build people who are early career scientists now into authorities in 10 years and 15 years' time. So thanks very much.
Talking about this in terms of interventions, not just measuring the interventions,
Yeah.
that does mean, if we're looking into big picture stuff, that we're going to have political data science, aren't we? I mean, I was somewhat caustic about Oxford Council, But we now have tools for people who want to take action with.
Yeah.
So we actually do we actually need to actually breed people who will do proper experiments and proper maths to deliver this?
Well, two sides to that. I mean, clearly, the data is going to be out there, and the more we get monitored and coded up, the more there's going to be. I mean, this does all belong to the citizen in some way, and so obviously there's some ethical issues around some of the things I talk rather flippantly about, but nevertheless, you know, they do have to be faced. And I think that, you know, within reason, with reasonable access, I think we should aim for that. I don't think we can carry on doing this just in universities or just in colleges.
Did you always just use the Twitter data set? And if so, did you cater for sampling bias of the people who would use Twitter? You know,
No, this only represented the self-appointed people using Twitter.
Okay.
Right?
And
The thing we were trying to get over here was we're faced with labelled graphs, labelled by each city, which did differ on orders of magnitude. And there didn't seem to be any off-the-shelf ways to really compare things differing by orders of magnitude. So this is a nice one because it would allow you to, where Q is any measure that you can calculate. So it was limited to this, and this is what we've made available. But clearly we could have gone with a number of other things.
so basically it was intentional. It was intentional. The difference in the sampling of the people who would use Twitter in the coming up with your maths.
Yeah, so a lot of my work goes to the advertising industry. So Des and I do a lot with digital advertisers. And actually, I know that at the research councils, if you apply for money off the research council, they say, well, it doesn't represent everybody, therefore you can't use this. But the advertisers don't care, you see. They say, well, it's that 18 to 25-year-old group that we can't get to, you know, but they're all on Twitter. So in a funny way, it's exactly where you want to go if you're working in digital media and advertising. But if you want to say something outside of that social, we're saying nothing here because they're clearly not represented at all.
Could you do it for countries?
Sorry?
Could you do it for countries?
Well, yeah, we can. I mean, so we have thought about that, and a number of applications. Getting the data is expensive now, so you've really got to have a good reason to pull all this, because you know we kind of need every tweet that's geo-referenced, and that's expensive. And of course, Twitter aren't exactly making loads of money, you may have noticed. So I think they need to be a bit more friendly to those of us who might put a bit of innovation at the data exploitation end. And those are ongoing conversations. But yeah, I mean, there's a possibility there. There are also sort of security applications of this, which are also, you know, I mean, we can see everything if we care to go and get the data. It's not trivial to get the data and clean it up, actually. So we couldn't do that in a maths department. Who would get a data set and clean it up? I mean, so you really, you know, we really did require some professional expertise to sort the data set out before we could deal with it. But so that made the data expensive, I would say.
This is sort of half a question and half a comment,
Right.
is that it just seems to me the safe spaces thing now has come up twice. So what it seems to me is that, let's say that we make safe paths. Actually, if we do that passively, then we're going to deepen divisions because we're actually going to render some bits of the urban landscape
We're giving them up.
more desolate and
Yeah.
abandoned, etc. So it seems to me, ethically, we really don't have a choice if we're progressives, is that we've got to do both, collect the data and think about intervention, because otherwise it's asymmetric, you know, it's going to worsen.
Well, I like that, but I'd also, the counter argument we learned from Oxford is that we're all, you know, there is different communities moving past each other and they're not connected at all. And I mean, we sort of wondered at time of year when all the kids are in school, at least everybody goes and stands in the playground together, right? But when the kids are out of school, arguably in the summers, maybe there is greater division in cities. There are also warm nights and beer, so, you know, but I mean, yeah, that does need thinking about. But what we'd really like is to be in the position where we could have some intervention and we could use this sort of thing to just passively monitor whether in fact there was greater integration or less integration. I think that would be a really good way to go. And then we'd be right back to how do you compare one data set with another? What's changed kind of thing, these sorts of questions. which could be answered by other things too, persistent homology, data clouds, all this, lots of other things that you could do. This is only one game in town, and probably not the best.
Just flipping it around, if you were the managing director of Twitter UK Limited, and you see your graph about the 10 cities, what would your strategy be regarding your product?
Okay, so I'll give you a quick example. If we knew where everybody was, I suppose we've got the network of London in front of us, and we knew where everybody was who used Colgate toothpaste, they'd all put their hands up. Actually, that's more or less a random pick. We all use toothpaste. We never talk about it. We don't ask each other which brands we buy. It's the same with asthma. If you say who's got asthma, they put their hands up. That's a random sample by vertex of that. So actually, if you want to talk to the asthma sufferers or the Colgate toothpaste users, you're broadcasting. You've got to talk to everybody. Get on the back of a bus, get offline, right? If you go for Jaguar cars or other kinds of high-value things that their owners like to talk about, they also go to the same golf clubs. It doesn't matter why they're all bunched up and things like that. But actually, there's obviously a whole load of knock-on, a lot of buzz in the trade and that kind of thing. So one of the things we could do is rank order all the brands in the country by the disproportionateness of their buzz. I mean, that would be good, because when advertising companies ran campaigns, they'd say we've increased the size of your footprint and we've actually increased its sort of connectivity or density or something. You've gone from 38 to 31, right? And the owners wouldn't say, what does that mean? They go, great, we've gone from 38 to 31. It would become de facto. They need to make sort of de facto measures that would be performance measures for advertising campaigns. That's what I'd do. And they could do that. Dead easy. Look, everybody, it's been lovely having everybody come along, but I just want to spend a few minutes where we go around and ask you guys, what's your feeling about all this? At the ATI, we want to have a thread which is around urban analytics. Clearly, we're aligned with some of the government things I talked about there, GCRF, spending large amounts of money working here and overseas. Clearly, it's of interest to some industries and not of interest to other. How does this strike you really as a theme for research and something that you'd be involved in or that you are involved with? Let's have a few comments from the floor. Don't be shy. Yes, please.
I'm just wondering how much of this research is informing policy? Because I came here, I've heard about in the realm of smart cities, pollution modeling or self-driving cars, things that will
well, not
make
enough of
cities.
it's informing policy, that's my view. Particularly, we've got this thing where, I'm going to speak against the air pollution thing for a minute. Right, so air pollution we can monitor if we've got the sensors in there. It's really just a question of having all the sensors there and things like that. And then what do we do about it? Well, you say, well, we've now increased, where I live in Henley-on-Thames, we've now increased the quality of the air by holding cars back up Remenham Hill. How do I feel about that when I'm trying to get home to watch Manchester United? I don't want it. Right, so unfortunately the civic goals are in direct conflict often with the citizens' goals, and that doesn't, always shine through. But at least if they're going to have fact-based policy, then they're going to have proper data and proper analysis of it. That's my view, really. So we can have the argument about citizen or civic goals. We can have, but I mean, fundamentally, more of us who are trained as data scientists within silo have to develop some skills to go and influence policy and things like that. And I know that at the Alan Turing Institute, we're going to have a sort of policy unit where we can get some of that training and get some of that, because otherwise we're going to be leading it to the MBAs and others who are just turning up and saying whatever they like on the basis of, a good degree. How shocking would that be? So I think we do need to get data scientists into that, but what we mustn't do is just constantly spout data science. We've got to meet them halfway and understand the nature of the policy questions. And that's quite difficult, but I think it's something that we can all do as data scientists.
Speaking of engagement, I'm Vice Chairman of the Conservative Technology Forum, and what we observe, just from being I'm both sides of the fence, but when I stand the other side of the fence, is it's basically people who are trying to sell us stuff who actually turn up. Twitter, we have Twitter members, or almost everyone that's a corporate member of our group or actually a member of our group, is a firm you will have heard of.
Yeah.
And what we don't have is academic level. You know, people just coming and telling us interesting stuff we can try and shove in a report.
Yeah.
And we do get the impression, speaking quite brutally, people don't want to speak to us as much as we want to listen to them. We've had to more or less mug people to try and get engagement. And I think part of that is a slight fear that what they're saying won't make it into policy, because A, it's true, because it doesn't always make it into policy, but B, if you don't try, it really doesn't happen. And people do need to have a go, and if they don't, it doesn't work, it doesn't work.
Yeah. No, this is right, but I mean, there's a pipeline problem in that for too long we've sort of siloed our disciplines, and success in mathematics looks like doing more mathematics, and there's a career there, a very good career, I think, for people who want to be commentators, who want to be policy advisors, who want to be journalists, actually, that have this deep data science background. I think there is a need for more rational umpires. It's dangerous because you might feel as a career you might get pulled into one argument or another, and you know. But I think there is a need for the sort of rational umpire in all this, particularly because a lot of the results that are going to come out are really going to be uncheckable by human minds. I mean, that's an ethical issue we haven't really got time for today, but you know what I mean. I mean, it's not as if we can go and get all the data, you know, that Google's got and just check what they're telling us. Is it? Because even if they give us the data, it takes us a month of Sundays to unwrap it. So I think that once data and alleged insights from data, and that's an ethical thing. So one of the things that I've been thinking about this year quite a lot is that the importance of placing ethics within data science education and understanding the role of whistleblowing, that kind of thing. Because if you're not if you're in a company, then sometimes bad things happen in companies for good reasons, Frankenstein type reasons, and someone needs to tell someone on the board in words that they will understand, because it's shareholder value that will be lost there. They won't just get hit over the wrist with the ethics committee. They lose shareholder value. Ask Volkswagen.
It seems to me that there's a lot of data in online petitions and so on.
Yeah. Well, there's quite a lot of analysis of that. I do know at the Oxford Internet Institute, they've written papers on the whole petitioning process in terms of what it's reflecting, the moods that it's reflecting. And Cameron was always one step behind public, wasn't he? He was always never could quite be there at the right moment. And now we live in a 24/7 kind of world where over a weekend 1 million people can sign up to something. That kind of changes things for politics and policy wonks, really.
I see why you're shaking your head, because obviously those petition people are hardly a random sample, are they?
No, they're not.
But
I mean, they have that ability.
But I think it's not just a question of what they sign up to, it's a question of word clouds of what they put in their comments.
More people in the first week signed up for Spandau Ballet's Gold becoming the new national anthem than Trump not coming to England.
Well, there we have it. There we have it, ladies and gentlemen. Okay, look, let me just finish it off there, look, because I want to continue this over drinks, but we do all need a drink now. We've been very good. We've sat and listened. I want to say thank you to the organisers here, and Chanuki, and thank you to the Royal Society for putting this on. When you're on the way home, the good news is that we've got a lot of people in this room that want to work in this area. Look, we've got to get this community going. And there are going to be opportunities. I mentioned some of them for funding both internally and externally in the country and out of the country. And so this is kind of an exciting area of growth for us. But we need to be imaginative and think about experiments which are going to have an impact, which are going to get us into the room when big stuff's decided. Okay, and that's the challenge for us. We've got to get out of our comfort zone and maybe meet some of the policy people halfway. Thanks very much for organising this.